Welcome everybody to our fifth talk of the virtual exchange seminars in quantum mobile networks. As usual, before moving to today's presentation, I would like to ask the audience whether there is any doubt or any question regarding the previous presentation. For the students, as usual, you will find links in the chat for the exercises related to this talk and the evaluation sheet, as usual, with deadline for both on Wednesday, as usual. So today's talk is titled Performance in Quantum Mobile Networks, Capacity, Delay, and Buffering, and will be presented by Alice Manyi Lavarenne from the University of Bern, Switzerland, and from Nogueira Ribeiro from the University of São Paulo, Brazil. The duration, as usual, is 30 minutes and will be followed by the usual question and answer session at the end. If you have questions, you can either type them in the chat and I'll take them at the end of the presentation, or you can directly ask the presenters at the end. So the first presenter now may share the screen, may share the slides and start their presentation.
Yes, that's me. Can you all hear me well?
Yes.
Okay. Okay, does that work?
Yes, for me it works.
Cool. Okay. So welcome everyone. We are doing today's talk in performance in quantum mobile networks. We will talk about more specifically capacity, delay, and buffering in terms of performance. And I will start with an introduction and motivations. So as I'm sure we're all aware of, all classical networks have been in the past decade, 2 decades, a very integral part of our daily lives. And since quite recently, we also were able to develop quantum network technology.
Excuse me, Alice, could you put your slides in full screen?
Sorry. I don't know how to, I don't know if I can do this in PDF.
I think it's Control L or Control Enter or Alt Enter.
Okay, sorry.
Yeah, okay, good.
Better.
Perfect. Okay. Thank you.
No worries. Yes, so quantum networks, which offer advantage, especially in terms of increased security, but also possibly performance, but also raises unique challenges due to the nature of the technology. For example, the necessity to store quantum states into quantum memories, in quantum memory. And we can also talk about more specifically mobile quantum networks, which we have to consider additionally that the nodes are mobile in comparison to classic quantum networks. We'll start talking about performance by first mentioning some physical limitation or some things that have been actually already addressed in the seminar. So I'll go over it quite quickly. So we also have channel noise, which in general is the random fluctuation or interference that affect the signal as it travels through the communication channel. In the context of quantum networks, it refers to any unwanted interaction between qubits and their environments. This can cause decoherence and loss of transmitted or untransmitted information. And there are various possible sources of noise, such as thermal fluctuation, electromagnetic radiation, and any external environmental factor. Kind of linked or in the same field, we also have signal attenuation. So the weakening or the loss of signal strength as it travels through the communication channel, sorry. This may be due to absorption, scattering, diffraction. We cannot do classical signal amplification as due to the no cloning theorem in quantum technology. So it's not possible to clone the particles, but instead we can use quantum repeaters. Yes. in terms of more classical performance, we can also talk about packet arrival process. This would be the way in which quantum information packets are generated and transmitted between nodes. This packet arrival process can affect the overall performance of the network, including the latency and throughput of packet delivery. And it is an important factor to consider when talking about performance. How the packets are transmitted can depend on the networks. We have the mobile ad hoc network, so where packets can be generated by user devices such as smartphones or tablets. And their transmission can be triggered by user actions such as sending messages. We have, of course, the quantum cellular networks, which uses the infrastructure of classical cellular networks and provides secure communication for mobile devices and other wireless devices in a cellular network. And finally, satellite-based quantum networks, which simply use satellites to distribute quantum information over longer distance. Other factors that may affect performance that I'm not going to go into too much detail could be node density, so how much nodes in a specific surface area, the transmission radius, queuing policy, which my comrades will talk about a bit more about later, or quantum switches. I'll just sort of clarify what we mean when we talk about those performance metrics. So capacity, delay, buffering, capacity or transmission capacity, simply the measure of the maximum amount of data that can be reliably transmitted over a wireless communication channel. The delay would be the time it takes for a packet of data to be transmitted from the source to the destination. There's several types of delay. Buffering would be the process of temporarily storing data in a buffer or a queue before it can be processed and transmitted to its destination. To talk about capacity, I chose to sort of review this paper from Harney, Fletcher, and Pirandola. So end-to-end capacities of hybrid quantum networks. That kind of does a lot of things. It's quite a long paper, but most importantly, it creates this formal framework, a mathematical framework for studying capacity in quantum networks. And it also aims to study the limits of communication in free space quantum networks. So more specifically, it's in the title, right? Hybrid quantum networks. And it does that by analyzing or reviewing several possible types of configuration of hybrid networks. Obviously, when we talk about the mathematical framework, it's a lot of math. Here is just like, for example, a small part of it, that is the performance of quantum networks over fading networks. So fading refers to the attenuation, distortion, interference of a transmitted signal that can be caused by various factors. And it is one of the major challenges of wireless communication. And here we have the equation that is used to measure this. So at the top we have BM, which is the multipath capacity the multipath capacity quantities. So the capacity of a single communication link, and down there is LM. It's the thermal noise. And CM would be the multipath network capacity, or the capacity of the entire network. And we can see how LM and BM are the upper bounds of the capacity. The paper then goes on to compare different types of configuration in terms of hybrid quantum networks. So for example, we have fiber satellite configuration. So a fiber-based community networks interconnected via satellite network backbone. The advantage is that it is immune or less sensitive to atmospheric decoherence because the optical fibers are insulated from the atmosphere, and because the signal travels through the vacuum of space. But the range could be a bit more limited. Here we have a graph that's proposed in the paper. Sorry, on the top left, we had ZB max, which is the maximum inter-satellite separation. Under we have Dmax, which is the maximum fiber length, and on the x-axis we have the capacity. We have two different setups as well, and two different scenarios, which are represented by the full lines and the dashed lines on the top graphs. And so this is more about how satellite fiber networks have certain constraints in terms of physical setting and network property. Sorry, I lost some notes. So we have they plotted the maximum fiber length and the maximum inter-satellite separation for a specific desired capacity or flooding capacity. And they found that there is a maximum fiber length allowed within a user community and a maximum inter-satellite separation allowed through the backbone network. If we keep going a little bit, we have this fiber ground-based configuration. So a mix of fiber channel and free space channel, where the goal is a bit the best of both worlds, with fibers that are more immune to atmospheric decoherence, although yes, and the ground base or the free space channels that can reach a longer range or a wider range. And so the aim is to do, or like they propose to do, ground-based networks for long distance links and fiber-based networks for local links. And here we also have a graph, so with Dmax, which is Dmax, which is the max fiber length, and down there is the max link length. And this shows that for a given architecture, there exists a maximum fiber length permitted within a user community, and the maximum maximum inter-satellite separation. Yes, and now I will give the control to Andre, and he will talk about delay in hybrid quantum networks.
Thank you.
Hello, can you hear me well and see my screen?
Mm-hmm.
Yeah. My name is Nogueira Ribeiro. I am an undergraduate student from University of São Paulo, and I will start presenting about quantum queuing delay. This part of the presentation is about the quantum queuing delay article made by these authors. First, queuing delay has significant importance for quantum networks. That's because quantum states interact with the environment and lose a significant amount of information. So if there is a big delay, there is a higher chance of corrupting the quantum state. Another challenge is to due to the particularities of quantum properties, there are just a few studies in the area, what contributes to the existence of many open challenges. The fundamental challenges are to maintain consistency with the theoretical realizations and practical restrictions, given that in this context, many articles abstract the physical implementation, what creates a gap between the theoretical and the practical part. Yeah. Another challenge is to exploit the properties specific to quantum nature for developing efficient policies and algorithms. Now I'm going to introduce the system used in the article. And the system is composed with the quantum node that's here and a collection of receivers here. The quantum node is composed of an entanglement generating platform here, an entangled memory here, and any quantum data queues, where n is the number of receivers. So there is 3 data queues here and 3 receivers. Each data queue is associated with a receiver, and an important point is that they assume that the data can be stored perfectly for an infinite time in the data queue. For the entanglement generating platform here, you consider for making attempts to generate entanglement qubit pairs between the platform, between the node, in the platform and the receivers. And it's important to say that the platform doesn't have the capability of storing the states. So in the article, they consider a discrete time, and they said that in the next slot of time, if the qubit remains in the platform, it corrupted. And finally, for the entangled memory the entangled memory is used when you attempt to make the entanglement generation, and if it succeeds, the quantum node will use this entanglement qubit pair immediately, or will move to the entangled memory for the future use. And now I'm going to show what is a queuing discipline. And normally, the queuing policy follow these steps. First, the arrival of the package, then the queuing discipline and the service time to execute it, and then the departure of the customers. Here is some possibilities for the queuing discipline with the model they used in the article. The double green lines represents teleportation here, and the dashed line represents entanglement qubit pairs. So in the first column here, you can see that the platform made the entanglements between the qubits on the platform and the receiver for the purple one and for the blue one here. Another thing is that this arrow means that you can move this qubit from the platform to the entangled memory for future use, as I said. And another thing here is that this green line represents the teleportation. So you use it to transmit the information from the data queue to the receiver. And it's important to mention that before the teleportation protocol, here occurs an entanglement swapping to establish an entanglement between the qubit on the data queue and the receiver. So after that, the teleportation protocol is executed, and you can transmit the information from the data queue to the receiver. And in the middle column here, it's shown 2 possibilities. You can discard the purple qubit from the platform. You probably choose this because there isn't any data on the data queue referred to the purple receiver. But as I showed in the first column, you can also move the qubit from the platform to the entangled memory. And in the last column, it's shown that you can make the teleportation protocol with qubits on the data queue and the entangled memory. In that case, it's shown the future use of the entangled qubits that are in the entangled memory. The teleportation protocol here works exactly like the protocol here. it's possible to transmit the information from the data queue to the receiver by first making entanglement swapping and considering that those 2 qubits on the entangled memory are entangled with the receivers. Finally, here, the article considered that if any data arrive at the data queue when the data queue is full, you have to discard it. And here it is what the image is showing that is doing with the red qubits. You are discarding it. So resuming, the queuing policy is responsible to choose what to do and when. For example, here you can choose to move the qubit for the entangled memory or discard it, or you can choose which data queue have some preference at a given point, which entanglement will be done, which qubits you will perform the teleportation protocol, and that influences the delay, because if you have a good queuing policy, you have less delay. So the choices you make influences the final delay. And in the article, they use a dynamic programming with a dense mathematical background to establish the queuing policies. And the result they get is an upper bound for the average queuing length. And this bound implies that the average queuing delay can decrease exponentially with respect to the memory size of a node. This image here is from the article, and you can see exactly that. In the horizontal axis here is memory size, and in the vertical axis here is the expected average queuing length. And the red line here is the upper bound that they determine. And it's shown that as the memory size increases, the expected average queuing length decreases exponentially, given that the graphic is in logarithmic scale, yeah? So, and that's good because the queuing length is directly connected to the queuing delay. So as the memory size increases, the queuing delay decreases exponentially. And this is the metric that they use, is like the complexity of related to the queuing length as the memory size increases. And now there are some open challenges in quantum mobile networks. First, it's important to remind that the queuing policy remains the same for quantum mobile networks because it's an algorithm, yeah. So, and that there is other kinds of delay, for example, associated with the transmission topic covered by the last 2 presentations too. And it's important to consider these other types of delay. One challenge is that the hardware needs to fit into restricted space, because you cannot have a big structure in the mobile scenario. Another challenge is the storage of quantum states without losses. And in the mobile scenario, you have to consider movement. And movement can also contribute to corrupt the quantum states. It makes the things worse. In the same topic, another problem is the coupling of qubits into and out of the material systems used for quantum storage. This process can also corrupt the quantum states. And an important point is that many articles abstract those 2 topics, and they do not deal with it. But if you want to do a real physical implementation, that will be a big problem. So you must consider it. And here are the references for our presentation. And finally, here are the 3 questions proposed by us. And that's it. Thank you.
Thank you both Alice and Andre for your presentation. So now we can open the question and answer session. So do we have any questions from the audience? Yes,
Yeah.
Andre.
Maybe I have a question. So you mentioned several times that sometimes in the paper they don't take into account some, let's say, practical or experimental parameters of which. So did you see? If you have, let's say, a quantum memory, so at some point you can quantify the performances of the memory in terms of decoherence time or speed you need to read or in and out. Did you came out in the paper if there's kind of normalized figure of merits, which then will allow to be taken into account in those kind of calculation that you've presented, where you estimate the efficiency of the network? I mean, maybe it's just a question for curiosity, so maybe not. Maybe it's.
Yeah, I'm not sure if I understand your question well, but in the article, like they consider the storage of quantum states in some points. For example, at the entanglement generator platform, and they quantify it like there's a dense mathematical stuff that they calculate. They consider the time of the operations and stuff like that. But in the other part, they abstract the quantum storage and consider it that this store perfectly for infinite time. And in the presentation, I consider in my part one article, the article that I mentioned, but in other articles, it's common. I saw that it's common to abstract this part. So in most articles, they does not consider the storage and they doesn't quantify it.
Okay, yeah, because usually in terms of memory, you have some a number which is called the fidelity, which gives you. So if you put some state in the memory, then the state you get out is not exactly the same. And the difference or the overlap between two will be the fidelity. So one will be perfect, and less than one, you have some degradation. And the other parameter will be, as you mentioned, so the storage time. So, and usually this fidelity decreases with time. The longer you wait, the worse you get the output state. But okay, so
yes, yeah, I understand. Yeah, in the article they don't consider it.
Yeah, so, which is the case usually doing theory, you try to take everything's perfect. So that's,
yeah.
Thank you.
Thank you.
More questions?
Okay, so I will have another. So for the hybrid network, so between satellite and fibers. So I just to get it, so at the end, their conclusion is, so if you want to optimize that or from A to B, and you can choose between fibers or satellite, then what they say, so you need a combination of both. So what was the main message?
Yeah, I guess that was, they were suggested that instead of just doing fiber or just doing satellite, to combine them to, I guess, to have a little bit of this best of both worlds type and try to take all the advantage from each technology, but avoid all of the inconvenience from each.
Thanks.
Okay. Any other question from the audience?
Yes. I suppose in the paper, the authors mentioned that the metrics, the performance metrics, they use transmission capacity, delay, buffering, but in the context of quantum networks, they include other metric like fidelity, decoherence, and the coherence and so on?
Yeah, in
As
my
a, oh,
the
sorry.
article that I read it, they don't include other metrics, but they consider in the dynamic programming model, they consider like practical implementation. So they put the time spent on the operations, the time to move the qubit, and oh yeah, it's nice to say that they consider that the entanglement, like they consider attempt to make entanglement. They not consider that every time they attempt, the entanglement will succeed.
Mm-hmm.
So they consider that to do the mathematical stuff about the queuing delay.
Great, great, thanks. And when they consider that the nodes could be in movement, they present some
No,
description.
it was difficult to find specific articles for quantum mobile networks. So the articles that I present was about quantum networks, but not mobile. And given that, I put at the end of the presentation some open challenge because I didn't found like specific to quantum mobile. So they not consider the restricted space. They not consider the movement that makes worse the corruption of the state and other stuff that is directed linked to the mobile scenario.
Okay,
Yes.
thanks, Andrea. Thanks, Alice.
So this is also part of the reason why there is not so much on this is also the motivation why we are doing this seminar. So this is the really the motivation why we created all of this, because after doing a bit of literature review, we saw that there was not so much at the intersection. So it makes sense that you didn't find a lot of papers. It was really to get a bit of creativity from the young students to see if they can find some connection between the two areas. It's still not so explored.
Yeah, that part of the articles was a little bit hard.
Yeah.
I didn't know what I can read and where I can find.
So we still have time for some more questions, if somebody has. Otherwise,
yes, if I may, a little bit more of a general question, though, just out of curiosity. Since we do not really have the opportunity to simply copy paste stuff in quantum as we do it in a classical, since this will change the state by simply observing it, we will change the state of stuff. So, how do you think, in the nearest future, will there be any opportunities to actually control and control the traffic or copy paste it or make some backups in regarding of quantum technologies? Thank you.
I mean, it's quite a big question. I don't really have an answer personally. Maybe Andre.
Yeah, I don't know exactly how to answer this, but I read like a little bit that there are some techniques to transmit the information, yeah, and also to I don't know if that's right, but as I remember, you can like they are developing some techniques to maintain the quantum states, like the teleportation protocol that you can pass in information, you can pass the state through another qubit, and by doing something like that, you can start thinking about memory. But as I said in the presentation, it remains a big challenge in their area. I don't know if the professors have a response like for the question, but yeah.
Sorry, I have read a tricky mess because there is no actual answer to that. There are some techniques that are sort of being served as a workarounds, but I just wanted to like hear. Maybe you have some opinions on that topic, and yeah, there is no certain answer for that yet. And thank you for your answer.
Okay, so more questions? Okay, maybe I can ask one. So this, okay, I have one for each. So maybe I can start from Alice. Is it in particular about the plots that you presented on this study on the performance of the links between fiber and the ground. There is a family of curves that is identified by KB, if you remember in the paper. So can you explain more what that KB means, and also a bit more explanation on the of the meaning of the x-axis? Maybe you want to share again if that slide.
Sure. Give me a second.
Yeah, you have there KB and KC in the plots, and so just reiterating the meaning of the x-axis and of these two parameters of the family of curves. So what does it go to change?
So the x-axis is the flooding capacity, right, as been introduced in the beginning of the paper through like all of their equations and the math they did about this.
What does it represent? So
the flooding capacity. Sorry, what was the question?
Yeah, this is of course. So I mean, practically, when you say flooding capacity, you mean the speed at which information moves through the network, the volume of information.
I don't. That's a good point. I didn't like look into it. I think it is the speed at which the information moves through the network. But yeah, I'm sorry, I didn't.
Okay. What about the parameter that identifies the different colors of the curves? We see that, for example, when we increase KB or KC, the curves tend to be flattened, so they move lower. So I guess this is some sort of gain parameter. What does it mean? Okay, I can give you some time. In the meantime, I can ask.
Yeah, I'm not sure. Okay.
So you can take a look at the other paper. So the question for Andre is a bit more generic. You talked about memories, right? Does the paper, probably not, but does the paper mention what are the materials, the physical materials to currently, the current technology to physically realize memories?
Yeah, it didn't appear on the article. And I also tried to find articles just about memory.
Yeah.
But
I want to make a quantum memory today. What should I go shopping for? What material?
Yeah, I really don't know. I also try to find like in what point we are today, like how many time we can store, but I didn't find that in an article or something like that. I searched on web and I found some information, but it didn't seem to be like a good source of information. Yeah.
Maybe on this, I'm pretty sure Professor Stefano, who has some more idea, maybe can tell us something about it.
Sorry.
Yeah. If you want to store any qubit, essentially, that is well, it's a two-level system. So that's why you use photons to make the network, and you encode into the photons this two-level system usually. So in polarization or in time or frequency, But if you want to store in a memory, so the photons, they fly like in a
Mhm.
classical computer, so you need some material. So ideally, the concept is you take one atom, and among the many level atom, you take two of them, and you define this as your two-level system. And so if the atom is in the excited state, it will be the qubit 1. If it is in a ground state, it will be the qubit 0. That will be the memory. Of course, it's not easy to capture an atom, to address it individually. Okay, but that is it's essentially how it's working. So people are working with atoms, some with ions, but which are essentially charged atoms, or something, some defect in a solid state. But the concept is always the same. So you have to address single atomic system.
Is there any material or any element that now is more that gives best performance to perform this type of storage, or still it's unclear?
Yeah, okay. So I'm not so much an expert in the memory, but you have a trade-off between. So in the material, with essentially you need a long lifetime. So you excite your atom and you want to stay in the excited state, not to decay. So that's on the one side. On the other side, you want to be able to access the atom. So you need something which interacts with light, but you do it usually with light to excite the atom or to retrieve the information in the form of a single photon. But because it's with light, and then it depends what you want to do with that light. So if you want that light to be sent in a fiber system, so it has to be at telecom wavelengths, which even restrain. So for instance, for telecom wavelengths, you have some erbium doped system when you have essentially like atomic-like system in a crystal. So.
Okay, thank you so much. Okay, so do we have an answer for the first question? The parameter of the curves?
Not really. I have the answer for the, I guess, the flooding capacity. That it was rather the maximum amount of data that can be sent.
Okay.
The number of bits per network use. As for the parameter, I'm not really sure. It must have made sense to me at the time. I think it's somewhat the number of backbone. Like I have this in my notes somewhere. That's the number of backbones nodes, but I'm not really sure what it means anymore.
Okay, not a problem. Is there any more question from the audience? I think we are almost done with time. We can take maybe one last one if there is any further question. Okay, so if there is no further question, I guess we can thank the speakers for their talk. So thank you so much for your effort and for presenting. And for today, this is it for the content. We will meet next Friday with the 6th talk, which is going to be about gossip protocols in quantum mobile networks.